So now we're going to look at the root mean square speed, and this is a concept we're going to need to progress further and do some of the algebra we'll do later in this topic. So we're going to consider n molecules of gas, which we're going to just label 1 to up to n, which each have velocity c1, c2, all the way up to cn, as I've drawn below. So here's particle 1 with velocity c1, particle 4 velocity c4, particle 5 velocity c5, etc., all the way up to particle n with velocity cn. So what's a good measure of the velocity of these particles? As in, if we wanted to talk about their velocities kind of as a whole, so rather than talking about the velocities of each individual particle, we wanted to give an idea of what they're all doing, kind of, like an average. What could we do? Well, we could just use the average speed of the molecules, which is just given by c bar. I'm going to use bars to mean average all the way through this, and we'll see it much more later. So that would be c bar equals c1 plus c2 plus c3, ... all the way up to Cn, and then we divide it by our total number of particles, which would be n. And that's our average speed, or our mean speed. But that's actually not very convenient for the equations that we're going to come across. So instead we're going to use the root mean square speed. And there will be a moment later when we'll realise why using the root mean square speed was so much more useful, especially when we come to essentially when we come to kinetic energy. We won't see that for a bit, but do trust me that this will be a lot more useful to us at the moment than talking about the average speed. So the equation for root mean squared is root mean square speed is as follows. So C RMS, which is how we write the root mean square speed, is equal to the sum of the squares of each of the individual speeds of the particles divided by the total number of particles square rooted. So just annotating that, we see these are the sum of the squares of the speeds, this is the number of molecules, and we've square rooted it, and that gives us our root mean square speed. And we can see why this is. Actually, the name really does just tell us exactly what we're doing, so we're gonna break it down in words. So the root mean square speed is just the square root, or the root, of the mean of the squares of the speeds. Which might seem quite obvious, but it's a really good way of thinking about it because it makes this formula a lot easier to remember. Because if you're told root mean square speed, you just do the root of the mean of the squares of the speeds, and that's it. It's just in the name. So this formula, which might look a bit complicated, is actually very easy to get just from its name. So increasing the temperature of a gas will increase the root mean square speed of its molecules, as we'd hoped. If we increase the temperature, we give more kinetic energy, so we'd hope we'd increase the average speed, but also we'd hope we'd increase this root mean square speed, because each of these speeds are the sum of these square speeds better increases when you increase the temperature, otherwise something's going very strangely wrong. And so this works. We'd expect this. So now we're going to talk about the assumptions of kinetic theory. So we're soon going to derive a formula that relates a gas's pressure to the root mean square speed of its molecules.
Hey guys, to continue watching this video and unlock hundreds of other super concise and exam board specific A-level physics videos, just click the Snap Revise smiley face. Join me today, and together let's make A-level physics a walk in the park.